This is how isoelectric focusing works. I'm going to use this gel as an example, and notice that we've loaded our samples in the middle of the gel. Normally, you're going to see the samples loaded at one end of the gel. I've chosen to do it in the middle because that's going to allow us to see how isoelectric focusing works in both directions. Let's say that the proteins on the far left gel are negatively charged, and the proteins on the far right gel are positively charged. The proteins on the left are going to migrate up towards the positively charged anode, and the proteins on the right will migrate down towards the negatively charged cathode. Notice that we have a pH gradient here labeled on the left. As proteins move down this pH gradient and migrate towards that positively charged anode, they enter into that lower pH. And as pH goes down, the hydrogen concentration increases. As that hydrogen concentration increases, certain functional groups on this protein will become protonated. And anytime something gets protonated, the charge increases. For example, if we have a functional group that's a carboxylic acid, it's going to be deprotonated with a negative charge at pH of 7. Eventually, as we go down that pH gradient, it's going to become protonated and lose that negative charge. So overall, the protein has become more positive. Let's say our protein had a net charge of -3, and this -3 is the overall charge. So this protein probably has some functional groups that are positively charged and others that are negatively charged. But overall, it's -3. Eventually, as we go down that pH gradient, some of those functional groups will become protonated, like what we said with the carboxylic acid here. The protein slowly loses that negative charge and becomes more positive, eventually becoming neutral with a charge of 0. And once it's neutral, it's going to stop migrating because it's no longer attracted to that anode. Exactly when that occurs depends on the exact pKa's of the functional groups of this protein. Because once the pH becomes below the pKa, those functional groups get protonated. Whichever pH causes the protein to become neutral is called the PI for that protein. The exact same principles can be applied to positively charged proteins. They migrate down towards the negatively charged cathode. As they migrate down, they're entering a higher pH, and as pH goes up, the hydrogen concentration decreases. As the hydrogen concentration decreases, certain functional groups will become deprotonated. For example, an amino group that's fully protonated has a positive charge. Eventually, once it reaches a high enough pH, that amino group would lose one of its hydrogens and become neutral. If our protein here started with a net charge of +2, eventually 2 functional groups will become deprotonated and the net charge would decrease by 2. That would make the protein overall have a charge of 0, and now it's no longer attracted to that cathode, so it stops migrating. At whichever pH that occurs, that is the PI for that protein. So for this one, it would be about 11.5.